Okay, so we're starting chapter 2. We are doing section 2.2, which is polynomials of higher degree. We skipped section 2.1 on quadratics because everybody should have gotten quadratics thoroughly in Algebra 1 and Algebra 2, so I just skipped it. We'll cover some things about quadratics as we go through this lesson on polynomials. So anyway, I skipped it to save us a little time. So 2.2, first of all, we need to set up our title page for chapter 2. So find your little tab that you put in a safe place and glue it on there. Start your title page. At any time you need to pause this video, then do so. Do what makes things work best for you. All right, let's see if I can make this. All right, so lesson 2.2 is on polynomial functions of higher degree. So you'll get these when you come back to school. Just leave space for them or sketch the little pictures to give yourself some ideas. So polynomials, what we need to know just to be able to look at a graph and know if it's a polynomial. There's two things to look for. First of all, they have to be continuous, so no holes, no breaks, no gaps. And the other thing is they have to be smooth, so they can't have like sharp points. So like this absolute value has a sharp point, it's not a polynomial. All right, so over here, this first piece, we're trying to just sketch a graph. And so if it's just an x to the fifth with no other terms, then it's going to look a lot like x to the third. It's just going to stretch. It's going to get kind of fatter between the ones, like close to the zero, but the ends are going to go really fast. Same thing if it's an even, it's going to look a lot like x squared. Remember that your normal things like a plus 5 on the inside moves you to the left. And again, kind of close to that zero, it's going to be a little fatter than normal, but it's going to go faster on the edges. All right, a leading coefficient test. First of all, we have to be in standard form, and we look at the leading coefficient. So when you have your polynomial, you're going to take this first term, provided it was in standard form. We look at the coefficient and the exponent. N is the degree, so that biggest exponent is the degree. So if n is odd, your ends go opposite, so one up, one down. If your exponent is even, then your ends point in the same direction, so both up or both down. When you look at that leading coefficient, if it's positive, the right side points up. If it's negative, the right side points down. So if I have an odd exponent and a positive leading coefficient, the right side goes up and the left side does the opposite. All right, so practicing that skill, we want to describe the right and left hand behavior of our graph, or the end behavior is what we normally call that. So for this picture, for this function, you're looking at this first term because it's in standard form. Your exponents are in order from biggest to smallest. So because that leading coefficient of 1/3 is positive, we know the right side is going to point up. Because the degree is even, we know that the other side is going to be the same. So if we sketch a picture, it's going to look like that. Some other junk can be happening in the middle. We're just talking about the ends of the graph. Both of them go up. So when we write our end behavior, it's as x approaches positive infinity, or as we move to the right, the function is going to go up or approach infinity. As x approaches negative infinity, the function approaches positive infinity, because both ends are pointing up. As we move to the left and the right, both ends go up. All right, so another one. For this one, we have a leading coefficient that's negative, so the right side goes down. We have a degree that's even, so the other side is going to match. So since both ends point down, when we do our end behavior statements, they both end with f of x approaching a negative infinity as we move to the right and to the left. All right, so one more. All right, so negative coefficient means right side down. Odd degree means left side is going to be opposite. So we have, as we move to the right, we go towards negative infinity, and as we move to the left, we go towards positive infinity. Alright, so next we're going to talk about real zeros of polynomial functions. So you may want to pause and write all this down and then go back and listen to me talk about it. So all of this is saying the fact that we know that a polynomial function of degree n, we know that that function has n real zeros. So if it was like something with a degree of 5, it would have 5 real zeros. Now it could have 3 real and 2 imaginary, but it could have up to 5 real zeros. It can touch the x-axis up to 5 times. And then turning points is maxes and mins, so the graph is going to have some curves, and it's going to be one less than that degree is the most that it can have. So again, if it's degree 5, then it could change directions 4 times in the middle of the graph. Your real zeros, this little guy is really just saying that zeros and solutions and x-intercepts and your factors are all basically the same thing. Your solutions come from your factors, but solution zeros, they're all the same thing. So repeated zeros and multiplicity. If your zero happens more than one time, then it's going to affect what happens on your graph. So if I'm looking at my factors, if I have one that only happens one time, then I'm going to go straight through the graph at that 0. If I have one that happens twice, then I'm going to curve and kind of sit on the graph at that 0. It's going to look a lot like a quadratic at that point. If I have something that's to the third, has a multiplicity of 3, then I'm going to wiggle through like a cubic graph looks at that point. That'll make some more sense as we go through these next few examples. Alright, so they want us to, first of all, just can you find zeros and the maximum number of turning points. Alright, so this guy has a degree of 3, so he can have 3 real zeros. Now again, he may have imaginary zeros, which come in pairs. Remember, crazy comes in pairs. So if you had imaginary zeros, then that would cut down how many real ones. But I think in this section, we're just dealing with things that have real zeros. Alright, so to find zeros, you make the function equal to 0 and you solve. Well, at this point, they haven't taught you a whole lot of tools to use to solve, so we're going to assume that things factor because that's all you really know how to do. So if you look at this, everybody has an x, so we can take out an x. Then if you see what you have here, you have a quadratic, which means we should be able to guess and check. Then we need x times x to get 36. I could use 9 and 4, I could use 6 and 6, but if I'm trying to add up to get 12, I think I need 6 and 6, both negative, because that multiplying 2 negatives gives me a positive. If I add the 2 negatives, I get that negative in the middle. Alright, so then we use the zero product property that says to make each of those equal to 0, and you get your solutions of 0, 6, and 6. So 6 has a multiplicity of 2, which means if I were going to try to graph this, I would know that I should turn around at 6 from what we were talking about a minute ago. So we found our zeros. We have zeros at, our x-intercepts at 0 and 6. Alright, we also are supposed to be figuring out the maximum number of turning points. Well, the maximum number of turning points is 1 less than the degree. So since we said the degree is 3, this thing can change direction 2 times. Alright, so next we're going to figure out how to get a sketch of a graph. Now, I know that your calculator is your best friend and we can use our calculator to see a graph, but we're trying to figure out if we can sketch a graph without a calculator. So, for this next problem, in your book it gives you a list of things that you need to do. So, if it gives you a list of things that you need to do to get the graph, you can't just jump to your calculator. You've got to give all of the pieces along the way. So the first thing that it's going to ask is for you to do a leading coefficient test to describe the end behavior. And at this point, I don't need you to write those as X approaches statements. I just need you to have an idea what the end behavior looks like. So our leading coefficient is positive. Our exponent is even. So we know the right side goes up and the left side matches. So the ends of our graph should look something like that. The next thing that they're going to ask you to do is to find the zeros. And multiplicity. Alright, so to do that, we're going to take our function, make it equal to 0, factor, we can't take a 3 outside, factor, so we can take out x to the third, that leaves us 3x minus 4. Use the zero product property, so x is 0 with a multiplicity of 3. Which means we're going to wiggle through that spot on the graph. And we take our other piece, the 3x minus 4 equals 0, solve that. We get 4/3, which, if we're going to plot that, it's probably important to know that that's 1 and 1/3. That has a multiplicity of 1, because there's no exponent on that factor, which means that we're going to go straight through on that one. Alright, the other thing that we need to do is find some more points so that we can get a graph. Because at this point, we know what the ends look like and where the x-intercepts are. So we know that there is a point at 0, and we know that there is a point at 1 and 1/3. We know that from both of those zeros, our graph is going to go up. What we don't know is what's happening in here, but because it's to the fourth, it could change directions as many as 3 times. So we need to make a table to figure out what's going on in the middle. Alright, so when we make that table, we want to know what's happening between these zeros. So I'm going to pick values between 0 and 1 and 1/3. So I know I need to know what happens at 1. So let's see if that's enough. So if we plug a 1 in, we're going to get 3 minus 4, so negative 1. Alright, and then at this point, you're welcome to use your calculator. You can plug in a 0.5. You can use your calculator to look and kind of sketch what's going on there. If we plug in 0.5, then we're going to get negative 0.3125, so roughly a point here. Alright, so using what we have and using our knowledge of our multiplicity, I would probably never even need to define at this point, because you know that this is going to go straight through. It's going to go down to here. We're going to curve, and we're going to have to come up and wiggle through that point. So having that extra point kind of helps you get that. But you also, if you just graph it on your calculator, can figure out what this looks like. Once you have this one point in the middle, then we should be okay. Alright, so number 8, we are going to have 2x to the third minus 6x squared. Alright, so leading coefficient test, you have to see that it's a positive leading coefficient with an odd exponent. So we know it points up on the right and the other side is opposite. So we know what the ends of our graph look like. Step 2 is zeros and multiplicity. So remember, take your function, equal it to 0. factor. So these are both divisible by 2. They both have an x squared. When you divide that out, you're left with x minus, not 6, x minus 3. So then we get these two from the zero product property. You have to take your factors and equal them to 0. And then we solve. Alright, so then talk about your multiplicity. So this was an x squared that gave us a 0. So it has multiplicity at 2. We're going to turn around at 0. This only happened once. It's linear. So multiplicity of 1, it's going to go straight through at 3. Alright, so then to find more points, we are going to make a little t-table. We put our x-intercepts, our zeros, on our graph. We know that we go up from here, we go down on this side. That's from our end behavior. And then we have to figure out some more points, and we can make a table. We can use our calculator, a little of both. So on our table, we're going to choose 1 and 2 because that's the numbers that fall between 0 and 3. And I'm wanting to know what's happening in here. This was at 3, not 6. Sorry. Alright, so if we plug in a 1 into our function, so just to show you how your calculator is beneficial, we know we can graph it and look, but there's also, if you go second graph, there's a table feature, and you can tell it you want to know what happens at 1 and what happens at 2, and it tells you answers for y's. Alright, so once you've typed it into y equals, if you do second graph, it gives you a table and you can put in what x's you want, it'll give you y's. So we know that at 1, we have a point at negative 4. At 2, we have a point at negative 8. Alright, so we also know that at 0, we are going to turn around. I know I drew my picture up, but it turns around and goes back down. And we know that at that 0 at 3, it goes straight through, so that's how we're going to draw it. Come back up and go straight through the axis. Alright, the last little thing that's in this section is the intermediate value theorem. We're going to talk about it. We're not going to do any problems that relate to it. We're just going to understand the common sense that that theorem is actually saying. So this says that if you have A and B are real numbers where A is less than B. So if we're on a number line, we have A is less than B. Alright, if F is a polynomial such that F of A is not the same thing as F of B. So if we're on the XY coordinate plane and we are making a polynomial and it looks something like this, then what we know is that, I don't know why I made that so random. We'll put A over here closer. Then we know that F of A and F of B are not the same thing. That's all they're saying. Then in the interval from A to B, there has to be a 0, is what this is really saying. That the function takes on every value between those two things. So basically what the intermediate value theorem is saying is that if I have a function and I find f of one number and f of another, if it changes from positive to negative, then it had to hit 0 in the middle. That's really all that's saying. So if I have a sign change in my y's, then I had to cross a 0 in between there, is the idea that they're really trying to get at. I mean, it really says that you're going to hit every number in between those y values, which is true. But what's important to us, sorry I keep sticking my hand under there, is that you're going to hit 0 if we switch from a positive to a negative or a negative to a positive. There has to be 0 somewhere in between. All right, ask me about that if that was thoroughly confusing when you come back to school, and we'll discuss it a little more.